Hi students, in this video we're going over section 5.5, Reflexivity, Symmetry, and Transitivity. So our goal for this video is just to discuss those three things for relations. Okay, on this slide we're going to go over the definitions formally, and then on the next slide we'll look at informal definitions for each of these. So our definitions here are going to be for reflexive, symmetric, and transitive. So we're going to let R be a relation on a set A. So in the previous video, we had a definition with a relation that was defined on a set A. And we talked about how instead of doing arrow diagrams, you end up doing a directed graph. So R is reflexive if and only if for all x in set A, x is related to x. 2, R is symmetric if and only if for all x and y in set A, if x is related to y, then y is related to x. And 3, R is transitive if and only if for all x, y, and z in set A, if x is related to y and y is related to z, then x is related to z. So in other words, informally, reflexive means that each element is related to itself. Symmetric means that if one element is related to another element, then that second element is related back to the first. And transitive means that if any one element is related to a second, and that second element is related to a third, then the first element is related to the third. And then this is what the relation is going to look like if it's not reflexive, not symmetric, or not transitive. So we still have our R relation on set A. R is not reflexive if and only if there is an element x in A such that x is not related to x. R is not symmetric if and only if there are elements x, y in set A such that x is related to y, but y is not related back to x. And 3, R is not transitive if and only if there are elements x, y, z in A such that x is related to y and y is related to z, but x is not related to z. Example 1, we're going to let the following relations be defined on set A, which contains the elements 0, 1, 2, and 3. We're going to draw the directed graph for each of these relations, and then we're going to determine whether the relation is reflexive, symmetric, or transitive. So for part A, we have R here contains 0, 0, 0, 1, 0, 2, and 1, 2. Okay, so we're going to start with our graph. I'm going to just list all the elements in set A, and then I'm going to draw arrows for each of these four ordered pairs, which are the elements in the relation. So we've got 0, 0, so 0 is related to itself, 0, 1, so 0 is related to 1, 0, 2, and 1, 2. So that's what your graph looks like. Now we're going to go through those three definitions. So is R reflexive? And that means that every element in the set A here has to be related to itself, which only happens with 0. 1, 2, and 3 are not related to themselves. So we're going to say R is not reflexive. And you just have to give one example, so I'm just going to say 1 is not related to 1. But you could also say 2 is not related to 2, 3 is not related to 3, but you only need one example. And now, is it symmetric? So that means, for example, if 0 is related to 1, then 1 has to be related back to 0, which is not the case in any of these. So we're going to say R is not symmetric. And just give one example. So one example would be that 0 is related to 1, but 1 is not related back to 0, right? You could also say that 1 is related to 2, but 2 is not related to 1. So just like, some different examples you can come up with in here. And then to show it's not symmetric. And then is it transitive? Can you show an example of where it would not be transitive? So this one is transitive. So R is transitive. I'll just put a little note here. If it were not, then there would be elements X, Y, Z in set A such that X is related to Y and Y is related to Z, but X is not related to Z. So it's transitive. I'll say so transitive by default, basically. You can't come up with an example where it's not transitive. Put it that way. All right, that's part A. Let's try part B. So for B, we have relation S, and it includes the elements 0, 0, and 1, 1. All right, so we're going to graph it first. So we've got 0, 1, 2, 3, and then we've got 0, 0, and we've got 1, 1. And that's it. That's our whole graph right there. So we're going to go through those definitions. Is it reflexive? It looked like it started out, right? 0, 0, 1, 1, but 2 is not related back to 2, and 3 is not related to 3. So S here is not reflexive. Or explanation, I'll just say 2 is not related to 2. You could say 3 is not related to 3. Just give one example there. And then, is it symmetric? Can we show an example of where it's not symmetric, right? So just a note down here. This is not symmetric. This is symmetric, right? So S here is going to end up being symmetric by default. So I'm going to say S is symmetric, because we can't come up with an example of where it's not. And I'll put a little explanation here. If it were not, then there would be elements X, Y in the set of A such that X is related to Y, but Y is not related to X. So symmetric by default. We can't come up with an example where it's not symmetric. And then, is it transitive? And if it weren't transitive, you'd have something like this, where X is related to Y and Y is related to Z, and then X is not related to Z, right? This would be transitive if this is here. If this is not here, then it's not transitive. This is going to be transitive by default, because we can't come up with an example of where it's not transitive. So I'm going to say S is transitive. And I'm going to put down if, like an explanation. If it were not, then there would be elements X, Y, Z in set A such that X is related to Y and Y is related to Z, but X is not related to Z. We can't come up with that example, so it's transitive by default. All right, part C, we've got relation T. So T here has 0, 0, 1, 1, 2, 2, 3, 3, 0, 1, and 1, 2 in it. Okay, so we start with our graph. There's 0, 1, 2, 3. All right, 1 is related to 0 is related to 0, 1 is related to 1, 2 is related to 2, 3 is related to 3. Then we've got that 0 is related to 1, and 1 is related to 2. All right, so that's what our graph is looking like. Is it reflexive? Yes, T is reflexive. Every element in this set here is related to itself. So I'm going to say, if it were not reflexive, then there would be an element X in set A such that X is not related to X. But that's not the case. You can't find any place where it wouldn't be reflexive. And then, is it symmetric? No. Right? You can look right here. You've got 0 is related to 1, but 1 doesn't relate back to 0. Same thing over here was 1 goes to 2, 2 doesn't go back to 1. So T is not symmetric. And our example is 0 is related to 1, but 1 is not related to 0 by the relation T. And then, is it transitive? No. T is not transitive. And this is because 0 is related to 1, and 1 is related to 2, but 0 is not related to 2. So that's an example of where it's not transitive. Example 2. Let A be the set containing the elements 0, 1, 2, and 3. Find a relation R on set A that is reflexive, symmetric, and transitive, and draw the directed graph. Here's 0, 1, 2, and 3. All right, there's going to be different ways you could answer this question, right? Different graphs for this. For it to be reflexive, each of these elements in set A has to be related back to itself. So these all definitely do need loops on them. And now it is reflexive. Now, if it's symmetric, you just have to make sure if you're going from one element to another, you have to make sure you go back to that element, right? If you don't do that, like if I don't draw any more lines, then it's going to be symmetric by default. So I'm just not going to draw any more arrows. And then if it was transitive, right, that means that if I have one element related to the other, to a second, and the second to a third, that first has to be related to the third, right? But if I do that, then I have to make sure also that I have these in here to make sure that it's symmetric. So instead of putting those arrows in and making the graph harder than it needs to be, just not going to draw any more lines, and then it's going to be transitive by default. So I'm going to leave it like this, and we're just going to have these 4 ordered pairs in our relation, and then it meets all those conditions, right? But this is one of many examples. So you can come up with other relations that are reflexive, symmetric, and transitive. I'm just going to leave it like that. That's the simplest graph that meets those conditions. Example 3. C is a circle relation on the set of real numbers. So for all real numbers x and y, x is related to y if and only if x squared plus y squared equals 1. So we're going to determine whether the relation is reflexive. And if it's not, you have to be able to come up with an example of where it's not. So C here is not reflexive. So by definition of C, this means that for all real numbers, x squared plus x squared would have to equal 1. This is clearly false. So I'm going to say, but this is false. So I'll do a little mini counter example. I'm going to let x be equal to 0. That's a real number, right? But then 0 squared plus 0 squared equals 0 does not equal 1. So it's not reflexive. All right. Is it symmetric? C is symmetric. So by definition of C, this means that for all real numbers, x and y, if x squared plus y squared equals 1, then y squared plus x squared has to equal 1 too, just swapping the order. This is true. This is true because by commutativity of addition, x squared plus y squared is equal to y squared plus x squared for all real numbers. I'll say for all real numbers, x and y. Last part, determine whether the relation is transitive. See if we can come up with a counterexample. This is not going to be transitive. Okay. By definition of C, this means that for all real numbers, x, y, and z, if x squared plus y squared equals 1, and y squared plus z squared equals 1, then x squared plus z squared would have to equal 1. But this is false. So we're going to do a little counter example. We're going to let x be equal to 0 and y be equal to 1 and z be equal to 0. Okay. Then x squared plus y squared equals 0 squared plus 1 squared, which equals 1. Okay. And y squared plus z squared is equal to 1 squared plus 0 squared equals 1. But x squared plus z squared would be equal to 0 squared plus 0 squared which equals 0, not 1. So it's not transitive. All right, we're done with section 5.5. I'll see you in the next one.